So just to start, this is a visualization of a beluga whale's call that was done by a graduate student who studies whales in the Arctic, which I thought was just really cool. Okay, so sound in the sea. So sound waves are waves in the physical sense, thinking about general physics, and they're produced by pressure changes between molecules. And so in order for those sound waves to move, sound needs to be transferred by the vibration of adjacent molecules. So if you've got more molecules closer together, or if something's denser, then sound is going to travel much faster. It's easier for it to move through those molecules. And so ocean acoustics, which is the study of sound in the ocean, has been something that's been around for a long time. So water is significantly more dense than air. And so because of that, the speed of sound in water or in the sea here is much, much greater than the speed of sound in air. And of course, like many things, because density plays a role here, and density is influenced by temperature, salinity, and pressure, then temperature, salinity, and pressure are going to influence sound. Because as I said, something that's more dense, sound can travel faster. So the velocity of sound in the sea increases by 1.3 meters per second for every 1 ppt increase in salinity. So if you look at this image on the left, you've got the speed of sound or the velocity of sound here on the x-axis. And you can see, so salinity, saline waters are more dense than fresh waters. And so these lines represent waters of varying salinity. And you can see as salinity increases, the speed of sound increases. The speed of sound increases by 4.5 meters per second for every 1 degree C increase in temperature. So as waters get warmer, you can see, let's just say for fresh water, as the water warms up, the velocity of sound in that water increases. And you can see then for the salt water, the same is true. As the water warms up, the velocity gets higher and higher. And then in the plot on the right, we're looking at sound velocity as a function of pressure. And so pressure was the aspect of density that wasn't super important. But when it comes to sound, it actually is, pressure becomes more important. So the velocity of sound increases by 1.7 meters per second for every 100 meters in depth. So basically for every change in pressure. So as pressure increases, as it goes deeper in the ocean, the speed of sound increases. So all of these differing impacts on the speed of sound, temperature, salinity, and pressure, result in the depth profile of the speed of sound having this sort of unusual shape. So here on the x-axis, we have the speed of sound increasing to the right, and then on the y, we have our depth axis, so going down deeper into the ocean. And so much like the temperature has a mixed layer, you can almost basically see like this little mixed layer here with the speed of sound. So the speed of sound is pretty fast at the surface because the temperature is high, it's warm, and so that results in a faster speed of sound. And then the speed of sound drops to a minimum within the thermocline. So you've got this thermocline here, and the speed of sound declines primarily because temperature is declining. And so if pressure didn't matter, then this would just keep going this direction as it got colder. But pressure does matter. So what actually happens down here is that the speed of sound starts to increase as the pressure increases. And so it bends back. And ultimately, the speed of sound is actually fastest at depth because of the great increase in pressure. But what you end up with is this region in the middle where the speed of sound is at a minimum. Its lowest point here. And this turns out to be really important. This is known as the SOFAR channel, where SOFAR stands for sound fixing and ranging. And so, again, here on the left, we're looking at the speed of sound as a function of depth, and we've got this feature where it hits a minimum and then increases again. And this SOFAR channel is where this minimum happens. And what happens here is that if you generate a sound in this channel, so this is your sound source, it ends up being focused and refracted from both above and below. So it wants to move in this direction, but it ends up sort of moving, and then it hits this region where the speed of sound is greater and it comes back down. And then it hits this region where the speed of sound is greater and it comes back down. So it ends up moving in this direction, but by sort of these bouncing oscillations. And this turns out to be useful because it means that the sound kind of gets stuck in this region. And so you make a noise here and it bounces, 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 but the thing is it keeps going. And so it can actually travel a really far distance. And again, what's driving this is that you've got pressure. So here we've got depth. So pressure is increasing, temperature is decreasing, and both of those result, the net at each place is that the speed of sound goes down and then ultimately comes back up. And it's this minimum region that creates this SOFAR channel. And this bottom plot is just showing sort of what real data look like as you bounce them around. They actually look pretty close to the idealized data. Okay, so the sound is focused in this SOFAR channel because the sound waves keep getting bent or refracted. So they bounce up higher in the surface or they bounce deeper, but they keep getting refracted back towards the region of lower sound speed. So above the SOFAR channel, it's warm, and so there's a decrease in the speed of sound. And below the SOFAR channel, the pressure causes an increase in the speed of sound. So they get trapped and propagated. And this is useful. One way in which this is useful is it can tell you something about temperature in the ocean or changing temperature in the ocean. And this is acoustic thermography. And this is a way to precisely determine travel times in water over large distances by noting how the speed of sound changes with temperature. And so what you do is you have a low frequency sound produced in the sound channel, and then it keeps going in this SOFAR channel all around the world, and you record it, you measure it. So in the atmosphere, we use a microphone. In water, you use a hydrophone, which is basically a microphone that works underwater. And so if you do this repeatedly and the oceans are warming, you should eventually start to pick up a signal that the speed of sound is changing. And this was explored using what's called the Heard Island experiments. And this cracks me up every time. So they released sounds from all these different locations. Everywhere you see a red line, hit this. And then they had a bunch of islands to choose from. And of course, they choose the one named Heard Island, where it heard the sound. And they put all the hydrophones on Heard Island. And so what they wanted to do was to see if they released all these noises at the same time, how long did it take to get to Heard Island? So the idea was, if you have this controlled man-made acoustic signal traveling all over the world's oceans and you detect them, can you sort of resolve, can you extract information from that, something about ocean temperature? And to cut a long story short, it turns out that no, it's the crux of it is that it's way more complicated than that. But nevertheless, it was an interesting and useful experiment. Okay, so then we have echolocation, which is something so we're moving away from man-made sounds here. So this is what marine mammals do. They send out noises and they use this to sort of see, quote unquote, in the ocean. And so they send out a noise, and then that noise is reflected back by objects around them, and it can tell the animal something about prey or obstacles. And this, what you're looking at down here, is what are called hearing curves. So hearing curves for marine mammals in water and hearing curves for humans. So the black line is humans. These are the frequencies that we can hear over and how well we hear. The green line here is a cat. And then the red line is an elephant. And then all these other lines are for other marine mammals. And you can see they hear at much higher frequencies than us, which basically, and there is some overlap, right? Which any of you who have done any diving or been lucky enough to be near whales, you might know that you can hear some noises, but you certainly can hear the bulk of what marine mammals are communicating to one another. And this is another way of looking at noise in the ocean. So this is super high frequency noises over here. And so these noises, like this yellow line, are things like water molecules bumping into each other, right? So way beyond what humans could hear. These blue lines are waves breaking and things like that. So again, fairly high frequency in this bubbles and spray area. And you can also hear rainwater. That's this purple line would be the noises from rainwater on the sea. And then in this sort of pink area, this is the frequency of ship traffic. And some of you might be aware, there's a lot of discussion about the impact of man-made noises, particularly from ships and military movements, on life in the sea. And that's this sort of ship traffic area here. And then there's also big things like earthquakes and explosions, which are higher, lower frequency noises down here. And so I encourage you, I posted a link to the DOCIT site. I encourage you to spend some time tooling around there and looking and sort of listening to the various natural noises and what they sound like and the various man-made noises. It's really fascinating. Okay, moving on to light in the sea. This is sort of representational images of divers. On the left is an open ocean dive, and on the right is a coastal dive. And you can see really clearly that you've got blue water in your open ocean and a much murkier and usually greener, sometimes even browner water in the coastal ocean. So why is that? So light comes from the sun and the electromagnetic radiation spectrum, and it comes in a variety of wavelengths. Here we're looking at wavelengths in the visible spectrum, so from about 800 nanometers here to 300 nanometers here. And all of these colors reach the surface of the ocean. Or by all of these colors, you could also say all of these wavelengths of light reach the surface of the ocean. But what happens is these long wavelengths, your reds, your oranges, even some of your yellows, are absorbed really quickly in the first meter or so of the ocean. And your short wavelengths, your purples, are also absorbed really quickly. But what's not absorbed are these blues and greens. And these blues and greens then penetrate deeper into the ocean, and it's the only light that's left to scatter back to your eyes. So that's actually why you see the ocean as blue or sometimes as green. So the actual total amount of light that enters the ocean depends on the height of the sun and how smooth the surface is, of course. A smoother surface will be able to allow more light through. But 65% of light entering the ocean is completely absorbed within the first meter and converted into heat. And that's where you get that sort of warm mixed layer of the ocean. 1% of light reaches the depth of 100 meters. And the longest and shortest wavelengths are absorbed first and last respectively, but they're also absorbed the most, which means that in the open ocean, blue light penetrates the deepest, which is why the ocean looks blue. And I think this figure shows it really nicely. On the left, you can see up to about the first 200 meters how the various colors are absorbed fairly quickly, leaving this blues and greens to be visible to the eye. And usually this 0 to 100 meters is considered the euphotic zone, called here the photic zone, but also euphotic. And from 100 down to about 1,000 meters, the technical term is the dysphotic zone. We usually call it the twilight zone. Much cooler, much easier to remember. And below 1,000 meters is the aphotic zone, A reflecting the fact that there's basically no light. So from 1,000 meters down, it's pretty much pitch black. On the right-hand plot, you're looking at light penetration in the coastal waters, and you can see it's a bit different. So there's a lot more stuff in coastal waters: phytoplankton, sediment, silt, soils. And so it's true still that the red and purples are absorbed fairly quickly, but in this case, the blues are also absorbed fairly quickly, and the greens are left to reflect off of all these different surfaces. And you can see the depth at where you pretty much hit no light is much, much faster as a result of the interaction with all the stuff in the water. So the color of the ocean is influenced by a lot of things. We just generalized and said that the open ocean tends to be blue. But it's influenced by the amount of turbidity, so how much stuff and silt and soils are there from runoff. The amount of photosynthetic pigment, so how much biology, phytoplankton are there. And the photosynthetic pigment, so when you have lots of biology, which we call highly productive waters, and it tends to be found in coastal regions and can be in upwelling areas, the ocean can look yellow-green, and that's because you're seeing all of these pigments. If you have not a lot of biology, and which means not a lot of stuff, not a lot of pigments, this is low productivity water, it can be a super clear, beautiful indigo blue, and that's found in the tropics and in the open ocean. One way that sort of super simple way to measure light penetration in the ocean, and if any of you guys stick around for honors, we'll do this on the field trip, is to use what's called a Secchi disk. And so that's what it looks like in the field. It's these black and white lines. So you put it on a line and you lower it into the water, and you ask a bunch of people to stand around to get a representative sample, and everybody decides when the disk is no longer visible, and you record at what that depth is. And the basic idea is that if you don't have a bunch of stuff in the water, you'll be able to see the Secchi disk really until it's quite deep. Whereas if you have a lot of algae and stuff in the water, it'll sort of rapidly disappear. And so you might measure the depth for here, in this instance, much, much higher. So you have these various zones in the ocean, just to go again. So you have the euphotic zone, which is basically the upper 100 to 200 meters, where most of the light is absorbed, not a lot penetrates past it. And then you've got the twilight zone between about 200 and 1,000 meters, where there's a little bit of light left, but not enough for photosynthesis, but there's some stuff happening. And then the bulk of the ocean is this aphotic zone, where it's just perpetual darkness. Not a lot happens, it's cold and dark. And life, excluding, of course, hydrothermal vents, which we learned about in the previous lesson, depends on sunlight. So phytoplankton use chlorophyll and other pigments to capture sunlight, and usually this is visible light. And they use that light to break bonds and create molecules and basically for life. And so when we talk about light in the ocean, what we're typically interested in is a portion of the light that can be used. And the portion of the light that can be used by phytoplankton is known as photosynthetically active radiation, or just known as PAR. So again, those of you who stick around for honors, in addition to the Secchi disk, when we drop instruments, one of the instruments that we drop will have a PAR sensor. And so it'll be measuring how much of that, what wavelengths are there, how much of it's available for radiation, photosynthetically active radiation. And if you look, this is a satellite image of chlorophyll down here. You can see regions with the darker color are regions where you've got lots of that chlorophyll. So the light is really important for the various organisms in these zones. So of course, phytoplankton productivity in the euphotic zone, that's most important. But it also can be important for predator-prey relationships and for animals that migrate in and out of the twilight zone. And then also for bioluminescence, which is super cool. These are bioluminescent organisms that can sort of mimic light. And I put a little video on Vula of bioluminescence happening in False Bay. If you ever get the chance to see it, it's an absolutely stunning phenomenon. And you can see here some in these still images. It's when organisms themselves are actually producing light by creating chemical reactions that happen. So they'll force a chemical reaction to happen, and then a flash of light will come out. It's used for all sorts of things, used to evade predators, used to attract prey, used for mating, used for communication. It's fascinating stuff. And then last slide here, light can also have negative impacts. So the shorter wavelengths down into your blues and purples and even beyond into the UV has a lot more energy. And at some point, it's more energy than our body or than other organisms can actually handle. And this is why, if you've heard of the ozone hole, it's a big deal. Because in the Antarctic, the ozone in the atmosphere usually sucks up all this bad radiation. But when there's a hole in the ozone layer, it lets this bad radiation through. And it leads to increased exposure to UVB radiation. And as people who live in the southern hemisphere, this is something to be concerned about. So just a note that not all